Good day, dear friends. Today, for your attention, is first lecture of new topic, distributed parameters element. This is so difficult but very interesting topic. In this topic, we will know that the parameters of elements really are distributed in space, and we will create a new part of the electrical engineering theory. In this lecture, we will make some conclusions about previous operations modes of electrical circuits. We will find out how it all began. I will take into attention the history of transatlantic telegraph cable. We learn about a concept of concentrated and distributed parameters of electrical element. We will make some definitions of distributed element circuits. So let me begin. First of all, let me represent some conclusions of previous topic of our course. In previous lectures, we studied the features and calculation of electric circuit in very different operating modes. First of all, it was a direct current mode, where the currents and voltages in the circuit did not change over time. Second one mode was alternating sinusoidal current mode, when the currents and voltages in the circuit change over time according to the sine law. And another one very interesting mode was non-sinusoidal current mode. We also know how we can calculate electric circuits in this mode. We also learned what is the steady state and transient modes of electric circuit and how we can find out the differences between them. We also have developed many methods for calculation electric circuits for both steady state and transient conditions. And today we can say that we know everything about electrical circuit. Or not quite all. Pay your attention, but we never before interested in where the main elements of electrical circuit, resistor, coil and capacitor, where the parameters of these elements are located in space. And today I'd like to start with some circumstance under which engineering realized that the current theory of electric circuit does not describe all electrical circuit. The year was 1856. At this time, all European capitals had telegraphic communication. Telegraph apparatus, you can see the photo of this apparatus on this slide, were connected to each other by overhead power lines. It was no problem to send a telegraphic message from Lisbon to, for example, Warsaw. The telegram reached the address in a matter of minutes. But communication between Europe and America across the Atlantic Ocean was a big problem. Can you imagine some telegraphic pole between the wave of Atlantic Ocean? Cannot you? So am I. So only way of communication was paper letters, which were delivered by steamships. About a month passed from sending the letter to receiving it. This greatly hindered trade operations, and so pupils looked for an opportunity to speed up this communication. In 1856, the American interpreter Cyrus Westfield, this is your photo, uh, created a joint stock company to lay a telegraph cable on the bottom of the Atlantic Ocean. This cable was supposed to connect the two closest points of American and European continents, the island of Newfoundland in America and the island Valencia in Ireland. The length of this cable was 3,750 kilometers. At that time, technology did not yet know polymers, so the cable consists from seven copper wires, insulated with gutta percha, a natural uh, rubber-like material. From the outside, the cable was wrapped with iron wires, which played both protective and second conductor roles. The weight of the cable was 550 kilograms per 1 kilometers of length. In August 1857, the first attempt to lay a cable from the coast of Valencia was made. However, this attempt was unsuccessful. The cable was broken and the storm forced up stop work. The next attempt was made in June on 1858 and was completed on 5th of August. And the 16th of August 1858, Queen Victoria of Great Britain and US President James Buchanan exchanged congratulatory telegrams. However, the transmission of the telegram from Queen Victoria to James Buchanan, which contains only 116 words, took more than 16 hours. This was due to the fact that the clear dots and dashes of Morse code in Great Britain were translated into unknown signals in the other end of the cable. At first, it was believed that the cause was some mechanical defect in the cable, but later this version had been rejected. The only version left is that we do not understand something about the processes taking place in the cable, but numerous attempts to understand this did not lead to success. Only the outstanding English physicist William Thomson, who also is known in science as Lord Kelvin, was able to understand the reason of this fact. He was the first to investigate the processes of propagation of electric signals in a long cable and came to conclusions of great practical importance. These conclusions made it possible to make the transmission of telegraphic messages across the ocean a reality. In fact, he created a new theory, a new branch of electrical engineering, the study of which U and R are beginning. Let's start. When we studying all modes of electrical circuits, we never took into account where exactly the main elements of electrical circuits, such as resistor, conductor, and capacitor, are located in space. Let's consider, for example, a real electric element. This element consists of quite a few turns of a wire wound on the core. At one time we said that such an element has all three parameters: conductivity, inductance, and capacity. It can be shown um, as equivalent scheme of this real element. This scheme consists of three ideal elements: resistor, inductor, and capacitor. And uh, the property of this resistance, are located only in this point of this equivalent scheme. Inductance are located only in this point. Uh, these ideal elements do not occupy space. They are concentrated in the one material point. How this can be? There is no need to ask, because these elements are ideal and do not really exist. But returning to the real element, we can no longer say that, for example, its resistor is concentrated in a certain point. This resistance is due to the physical resistance of the wire material from which this element is made, and this resistance is uniformly placed on the core. That is, resistor is distributed through the element. The same can be said about inductance and capacitance. Thus, we can talk about the fundamental distribution of parameters of all real elements. And now a completely valid question naturally arises. In what case we can use this idealization, that is, neglect the distribution of parameters? And accordingly, in what cases we should take this distribution into account? It is intuitively clear that the answer to this question must be related to the geometric dimensions of elements. If the dimensions are small, then obviously the distribution can be neglected, and it can be assumed that the parameters of such elements are concentrated in one point. But if the dimensions of the element uh, or electric line are large, then the distribution of its parameters must be taken into account. Everything is correct, but it is not clear what is small sizes and what is large. In order to compare the sizes of electrical elements, it's necessary to find a suitable criterion. It should be closely related to electricity, because taking into account or ignoring distributedness affects the calculation of electrical modes of operation of this element. As such a criterion in theoretical electrical engineering, the wavelength of the current and voltage that propagates in the line is used. Recall that the wavelength lambda is the distance traveled by the wave in the time equal t, moving at a speed v, and it calculates by this formula. Based on this criterion, we can say under which conditions we should consider the distribution of parameters and under which conditions we should ignore it. The distribution of parameters of n elements of an electric circuit should be taken into account if its dimensions are comparable to the wavelength of the electromagnetic energy acting in this element. This table shows the frequencies and wavelengths at which various electric devices operate. When we can say that the size of circle is proportional to the wavelength. Consider, for example, the electric cord that goes from your table lamp to the outlet. Its length is about 1.5 meters. Should we consider the distribution of its parameters when we calculate the currents and voltages in it? We will count the frequency of electric current in our lighting networks is 50 Hz. The period of current fluctuations is 200 of a second, and the wavelength of in our cable is 6,000 kilometers. Can we ignore a cable length of 1.5 meters at a distance of 6,000 kilometers? Of course, it is. Therefore, our cable is not a distributed element circle. Let us now consider the power transmission line that connected the western and eastern bords of Ukraine. According to the Wikipedia, the territory of Ukraine stretches 1,316 kilometers from west to east. As the distance 6,000 kilometers is comparable with this length. Yes, of course. It is impossible to not take into account these 1,316 kilometers compared to 6,000. That is, when calculating currents and voltages in this line, we must take into account the distribution of parameters. But is it necessary for distribution element circuit to be 1,000 of kilometers long? No, it all depends on the wavelength of electromagnetic energy, as we say. For example, the dimensions of a router are of our Wi-Fi router is only 6 centimeters. So we cannot ignore the length of antenna of these routers comparable with this distance, only 6 centimeters. Thus, the our new theory, which we are starting to create, will be applicable only to electrical circuits, the dimensions of which are comparable to the wavelength of the currents and voltages in them. In these lections, we learned the differences between the electric circuits with concentrated and distributed parameters. Now is time for short conclusions. In previous topics of our course, we didn't take into account that fact that the elements of electric circuits have some dimensions and the parameters are distributed in space. We can neglect the dimensions of electric only if these dimensions are much smaller than the wavelength of electromagnetic energy that propagates in this element. A typical example of distributed element circuits is an electric power transmission line. In theory of electric circuits, we studied early cannot describe electromagnetic process in the distributed element circuits. So it is necessary to create a new theory. The basis of new theory will be three known laws of electrical circuits. This is first and second laws of Kirchhoff as well as the communication law. In the steady state of the distribution element circuits, we can use only the two first laws, first and second laws of Kirchhoff. And to build a new theory, we need to find out what parameters characterize a distributed element circuits. This will be the topic of our next lecture. Thank you.